So this is part two of just narrating the slides on intermolecular forces, and just to quickly wrap up what was in part one, or just not wrap up, but just to quickly go back over to remind you. Intermolecular forces, we had referred to them previously in the class as particle attractions between particles, and we brought that into play talking about solids, liquids, and gases, and the relative strength of the attractions between particles and the kinetic energy. Now we can refer to those things as intermolecular forces. And so these are just going over what we talked about, just figuring out whether or not a molecule is polar. And so there's nothing here that we really need to talk about. And we're all hopefully getting to the point where we can draw a Lewis structure of something, look at it and decide, and use the little sort of rules I gave you on, okay, bent is always polar, trigonal pyramidal is always polar, tetrahedral, trigonal planar, and linear are nonpolar if the surrounding atoms are the same. They're polar if the surrounding atoms are different. Let's move on from that. And this just has to do with, again, with gases, liquids, and solids. And so this, and the point that I made in this slide, if you'll recall, that this black line is the covalent bond within a hydrogen chloride molecule. It is very strong. This red dot, dot, dot is the intermolecular force between two hydrogen chloride molecules. It is relatively weak. They are weaker than covalent bonds, but they have profound effects on the physical properties of the substances. And as we talked about, the intermolecular forces are all based on the concept that opposites attract. And we talked about how it can be possible. So we did talk about one specific intermolecular force, which was dispersion forces, and tried to describe how it's actually possible for you to have partial positive and partial negative charges in a molecule that's nonpolar. And so we talked about dispersion forces, which are temporary dipoles, transient dipoles, if you want to say. And this is a relatively weak intermolecular force, but it can be quite strong in molecules that have a large molar mass. And so we talked about the fact, for example, that iodine, I2, which has only dispersion forces between molecules, actually is a solid at room temperature. And we talked about the CBr4, which is also a solid at room temperature because it just has a really monumental molar mass. Okay, let's move on and talk about dipole-dipole forces. Dipole-dipole forces are a little bit easier to comprehend because we started this conversation by saying that that intermolecular forces are attractions between partial positive and partial negative charges. And you'll recall that if you have a polar molecule, it's got a partially positive side and a partially negative side. So it would be perfectly reasonable to imagine that there are electrostatic attractions between the partially positive end of one molecule and the partially negative end of another molecule. And that's just what this text says here. Dipole-dipole forces are stronger than dispersion force. This is an important point I want to make. When it comes to molecules that are of similar size and molar mass, then dipole-dipole forces are stronger than dispersion forces because dipole-dipole forces come from permanent dipoles, not from temporary dipoles. So if you're comparing two things that are very similar in molar mass and size, but one of them is polar and the other one's nonpolar, then the polar one is going to have stronger intermolecular forces because it has dipole-dipole forces. The example that's here is this molecule called acetonitrile. Its formula is CH3CN. There is a CH3 here. There's a carbon in the middle, and then there's a nitrogen on the end. The CH3 end is the partially positive end of the molecule. The nitrogen end, the blue end, is the partially negative end of the molecule. And you can see that this is just a schematic of solid acetonitrile. And you can see that when it solidifies, it lines up so that the blue end of one molecule is adjacent to to the CH3 end of another molecule, and that is true all the way through this entire schematic. And so the dipole in this molecule, the permanent partial charge separation, the nitrogen end, the blue end, which is partially negative, and the CH3 end, which is partially positive, that allows there to be electrostatic attractions between molecules. Not all polar compounds are identical because some, way back when, and I can't remember exactly when I said this, but some polar molecules are more polar than others. And there is a property here known as mu, which I'm not going to try and explain to you what it is. It simply says the larger the value of mu, the more polar the compound. So propane is essentially completely nonpolar. Dimethyl ether has some considerable polarity, acetaldehyde more. And then acetonitrile, the molecule we were just looking at, is very polar compared to these other two. You'll also, the other point that I need to make about these molecules is they're all very similar in size and shape and extremely similar in molar mass. And so the only difference in their physical properties is going to be down to the strength of their intermolecular forces. And you can see that as the dipole gets stronger, going from 0 to 1.3 to 2.7 to 3.9, the boiling point goes up, 231, 248, 294, 355. Increasing polarity, increasing strength of dipole-dipole forces. Rest assured, I will never ask you to attempt to calculate or interpret a mu value. I'm just using these here to try and illustrate to you the increasing polarity of these molecules. Okay, the third type of intermolecular force we want to talk about is hydrogen bonding. And hydrogen bonding is a particularly strong type of dipole-dipole interaction, but it can only occur between molecules that contain a hydrogen atom that is bonded either to nitrogen or to oxygen or to fluorine. In other words, it contains an NH bond or an OH bond or an FH bond. And hydrogen bonding kind of has it's a type of dipole-dipole interaction, but it is so strong that it has its own name. And the reason that it occurs is that if you have one of these bonds in your molecule, NH, OH, or FH, the difference in electronegativity between the two atoms in that bond is so large that that hydrogen atom is highly polarized, is very positive. And then it will go and find a nitrogen or an oxygen or a fluorine on an adjacent molecule and stick to it because that nitrogen or oxygen or fluorine is very negative. And so it's going to want to stick to hydrogen atoms from a neighboring molecule. I got some pictures of this, so it'll make a little more sense in just a second. But you can see that these are all very polar bonds, and so that is what allows them to engage in hydrogen bonding. So let's look at some pictures. I want to make sure I make clear what hydrogen bonding is and is not. The red dots are the hydrogen bond. The hydrogen bond is not the covalent bond between a nitrogen and a hydrogen atom in the same molecule. The hydrogen bond is the electrostatic attraction between the nitrogen atom in one molecule and the hydrogen atom in a different molecule, between the fluorine atom in one molecule and the hydrogen atom in another molecule, between the oxygen atom in one water molecule and a hydrogen atom in another water molecule. Once again, these are much weaker than the covalent bonds that hold the water molecule together, but they are sufficiently strong to obviously influence the physical properties of water. So much so that if you, as we get deeper into this, and particularly when I was working in the pharmaceutical industry, we talk about hydrogen bond donors and hydrogen bond acceptors. And water is a very unique molecule because it can donate two hydrogen bonds. It's got two hydrogen atoms on it, and it can accept two hydrogen bonds. It's got two non-bonding pairs on oxygen. And so in a ice crystal, you actually have, and they have, this image doesn't really show it, doesn't really give it justice. You can see some water molecules making as many as 3 hydrogen bonds, but if we were showing this more in 3 dimensions, you can see that each water molecule in an ice crystal actually makes 4 hydrogen bonds. And again, they are not covalent bonds. They are the electrostatic attractions that hold water molecules together with other water molecules. This is about the last time you're going to see or hear about hydrogen bonding in fluorine-containing molecules from me, because whereas there are an endless number of naturally occurring and synthetic molecules that contain an OH bond, and there are endless numbers of naturally occurring and synthetic compounds that contain NH bonds, there is only one substance in the universe that contains an HF bond, and that's hydrogen fluoride, and it's a very toxic substance. And so we're just not really going to talk about it anymore. We're just going to focus on OH and NH. And what the next slide is going to say, it's not only the case that you can get hydrogen bonding between one ammonia molecule and another, or between one water molecule and another, you can also get hydrogen bonding between a water molecule and a neighboring ammonia molecule, which is why ammonia is soluble in water. Or between, so here you've got the hydrogen of a water molecule, hydrogen bonding to the nitrogen of ammonia. Here you've got the hydrogen of an ammonia molecule, hydrogen bonding to the oxygen of a water. And there are almost endless combinations of these things that you can see in solution. And if you remember from biology about that it's hydrogen bonding that holds the base pairs together in the double helix of DNA, you'll recall that it is that adenine is paired with thymine, and you can see the hydrogen bonds here between an NH here and an N there, between an NH here and an O there. And you can also see that there are 3 hydrogen bonds between a guanine and a cytosine. Okay, comparing intermolecular forces, and this is going to be an issue with your homework. And so let's just for number one, all substances display dispersion forces, but there are a lot of substances for which dispersion forces are not the main thing. If 2 substances have similar size and molar mass, then the polar molecule is going to have a dipole-dipole attraction, and it's going to be stronger. And so pound for pound, dipole-dipole interactions are stronger than dispersion forces, and hydrogen bonding is stronger than dipole-dipole interactions. So that's the biggest takeaway. Hydrogen bonding stronger than dipole-dipole, dipole-dipole stronger than dispersion. But it is also the case that when you have a very large molecule, then the dispersion forces become very significant, and they kind of control everything. And I think this is my last slide, and it just compares 2 things we've already looked at in this video: propane, which is nonpolar, acetonitrile, which is polar. They have very similar in size and molar mass, and so it makes sense then that the acetonitrile, because of its dipole-dipole interactions, has a higher boiling point than propane. But if you get to CBr4, which has a similar number of atoms to acetonitrile, but is a completely nonpolar compound, because of its large molar mass, it actually has its dispersion forces are stronger than the dipole-dipole forces in acetonitrile. This is just now saying what I said earlier, that we can now substitute the term intermolecular forces for the term attraction between particles that we were using earlier in the year when it comes to comparing the kinetic energy and the intermolecular forces in solids, liquids, and gases. Okay, the homework assignment you're going to do is kind of similar to the one that you did over the weekend. You are going to simply take get a series of compounds. There are 10 of them. Sometimes the guy that I download these from skips a number when he's numbering things, but it looks like they really are 10. And so you're going to go the whole route here. You're going to draw a Lewis structure. You're going to determine whether or not it's polar or nonpolar. These are all things that are a fairly similar size. And so you can go very simply just say, if it's nonpolar, it's going to be dispersion. If it's polar, but the molecule does not contain an NH or an OH, then it's going to be dipole-dipole. And if it's polar and the molecule does contain an NH or an OH, then it's going to be hydrogen bonding. Thanks for watching.